We rely on cutting tools for just about everything. It's incredible when you think about it. They really do shape our world in a very literal sense.
I know, right? From the most basic things like a simple bolt to the really complex parts in a jet engine like a turbine blade, they're all shaped by these incredibly precise tools.
And the demand for these tools is only increasing, especially with the way manufacturing is evolving. The shift toward mass customization, making things specifically tailored to individual needs, well, that requires tools that are even smarter and more adaptable than ever before.
Absolutely. And alongside that, there's this massive push for greater sustainability in manufacturing. We need cutting tools that aren't just more efficient and precise, but also made using materials and processes that are less environmentally impactful. So how do we ensure these essential tools can actually keep up with all these demands?
That's the big question. And thankfully, there's a lot of really exciting research happening right now that's looking into just that.
Exactly. And we're going to delve into some of that cutting-edge research today.
That's right. We're doing a deep dive into a fascinating study that's exploring new materials for these cutting tools. It's all about finding viable alternatives to the materials that have been the industry standard for decades: tungsten, carbide, and cobalt.
Yep, those two have been the go-to for so long because they're incredibly effective.
Right. But as we'll explore, there are some significant downsides too, especially when you consider the long-term sustainability of the entire manufacturing process.
Absolutely.
So for all of you out there who are interested in getting a solid grasp on this complex field without getting bogged down in endless technical details, think of this as your shortcut.
We're here to guide you through the key takeaways, the really important stuff in this research. And we're going to do it in a way that hopefully makes it all a bit easier to digest.
Exactly. Our mission today is to understand why there's this pressing need to find replacements for the current industry standard materials, what those potential alternative materials might be, and how those new materials can be manufactured in a way that actually works for the real world.
Exactly. And our main roadmap for this deep dive is the thesis Tarancón.pdf that you, the listener, so kindly shared with us. So a huge thanks for that. This thesis really dives into some intriguing possibilities, and we're excited to break it all down for you.
Yeah, this is some pretty high-level material science, but it's incredibly relevant to so many industries and to the future of manufacturing in general.
For sure. And to lay the groundwork for this discussion, let's start with the fundamentals. What actually makes a cutting tool effective? What are those essential properties that it absolutely needs to have?
Okay, that's a great place to start. So when you picture a cutting tool in action, imagine it slicing through metal at high speed. It's under tremendous stress, and it's encountering a lot of friction.
Right. And to withstand all of that, it needs to be incredibly hard. Hardness essentially means it can resist wear and tear. It can stay sharp even as it's grinding away material.
Makes sense. So hardness is crucial, but is there a downside to being too hard?
Yeah, there's a catch. If a material is extremely hard, it can also become brittle. It's kind of like glass, very hard, but can easily shatter if you drop it. The same principle applies to cutting tools. If they're too brittle, they're much more prone to snapping or chipping under those intense forces.
Ah, so it's about finding that sweet spot, the right balance between hardness and toughness.
Exactly. We want a tool that can take a beating and still hold its edge. But it doesn't stop there. You've also got to factor in heat. Imagine the temperatures involved when a cutting tool is slicing through metal at high speeds.
Yeah, it must get pretty hot at the cutting edge.
Incredibly hot.
Yeah.
And as the temperature rises, even the hardest materials can start to soften. This can lead to all sorts of problems: reduced cutting efficiency, increased wear and tear, and even the potential for bits of the material being cut to actually stick to the tool. It's a messy situation.
So the ideal cutting tool material needs to be a real multitasker. It needs to be hard, it needs to be tough, and it needs to be able to handle extreme heat without losing its performance.
Precisely. It's a tall order, but over time, materials science has come up with some pretty ingenious solutions.
Right. So let's talk about the evolution of these materials. How did we get to where we are today? What were those early cutting tools actually made of?
Well, way back in the day, the go-to material was simply tool steel. It's a type of steel specifically designed to be harder and more durable than your average steel, but it still had its limitations.
Right. And at some point, they figured out how to make it even better, right?
Exactly. And that brings us to a pivotal moment in the history of cutting tools. Back in 1868, a metallurgist named Robert Forrester Mushet made a game-changing discovery.
Oh, this sounds intriguing. What was it?
Well, he found that adding tungsten to steel had a remarkable effect on its properties. It dramatically increased its hardness, even when it was simply cooled in air, which was a big deal back then. That marked the beginning of what we now call high-speed steel.
High-speed steel. So this tungsten addition was the key to allowing tools to operate at higher speeds.
Exactly. But there was still room for improvement. As industries like automotive started to really take off in the early 20th century, there was this constant push to manufacture things faster and more efficiently. And tool steel, even with a tungsten boost, just couldn't keep up.
What was the limiting factor?
Well, it was mainly the temperature. As cutting speeds increased, the heat generated at the cutting edge became a major problem. Tool steel would start to lose its hardness above around 700 degrees Celsius. It just couldn't maintain its performance at those temperatures.
So the demand for speed in manufacturing actually drove the need for even better materials. That's fascinating.
Absolutely. And that's where high-speed steel, or HSS, really came into its own. Think of it as tool steel on steroids. It incorporates significant additions of tungsten, as well as other elements like cobalt, vanadium, and chromium. These additions dramatically improve the steel's strength and, crucially, its hot hardness, its ability to remain hard even at elevated temperatures.
So HSS was a major step forward, allowing for much faster, more efficient cutting operations. But even HSS had its limits, right?
That's right. The relentless pursuit of even higher speeds and greater precision continued. And that brings us to another turning point. The invention of cemented carbides.
This is where tungsten carbide comes into the story. So how did that come about?
It's actually a bit of a roundabout tale. Between 1907 and 1928, a researcher named Franz Scalpi, who was leading a team at Osram, the light bulb company, was on a quest to find a substitute for diamond. They needed something to make dies for drawing tungsten wires for their light bulb filaments.
So their focus wasn't on cutting tools at all?
Not initially. They were experimenting with sintering tungsten powder with carbon, hoping to create a ductile material that could withstand the extreme conditions involved in wire drawing. What they ended up with was tungsten carbide, incredibly hard, but unfortunately quite brittle.
So a bit of a scientific detour that led to a major discovery.
Exactly. But then, a colleague of Scalpi's, Carl Schroeder, had this brilliant idea. He realized that if you combined this super hard tungsten carbide with a small amount of a metallic binder, like cobalt, nickel, or iron, you could create a composite material that was both hard and tough.
So that's the secret sauce of cemented carbides, that combination of a hard ceramic material with a tough metallic binder.
Precisely. And they figured out that the exact amount of carbon in the tungsten carbide was critical for getting the properties just right. They found that between 3 and 6% carbon was the sweet spot.
Interesting. So tungsten carbide was initially intended for wire drawing, but its true potential really lay elsewhere.
You could say that. In 1923, Schroeder patented this innovative material. Soon after, Krupp, a major German industrial company, saw the enormous potential of this new material for cutting tools. They acquired the patent and in 1927 introduced it to the world under the name Widia, which fittingly means like diamond in German.
That's a great name for it. So how did these Widia tools actually work?
Well, one of the key innovations was the development of replaceable cutting inserts. So instead of having a solid tool made entirely of tungsten carbide, which would be very expensive, they created these small replaceable tips made of the material. These inserts could be easily attached to a tool holder, and when they wore out, you could just swap them out for new ones. It was a brilliant solution for both cost effectiveness and efficiency.
And these cemented carbide tools really revolutionized the manufacturing world, didn't they?
Absolutely. They enabled much higher cutting speeds and offered significantly longer tool life compared to even the best high-speed steels. They really were a game changer, especially when it came to machining very hard materials like cast iron and hardened steels.
So tungsten carbide with a cobalt binder, or WC-CO as it's often referred to, became the industry standard for high-performance cutting tools.
Exactly. They even developed variations with titanium carbide added to the mix. These were initially introduced by Krupp under the name Widia X back in 1932, and they proved even better for working with steels, although there were some early challenges with how to effectively join these titanium carbide inserts to the tool holders.
Interesting. But it's amazing how this material that was originally intended for something completely different, drawing wires for light bulbs, ended up transforming the way we manufacture things.
Totally. And while we've seen the development of even harder materials since then, like cubic boron nitride and synthetic diamond, cemented carbides are still the preferred choice for the vast majority of applications where you need a balance of efficiency, precision, and cost-effectiveness.
Okay, so tungsten carbide, and specifically that cobalt binder, has been essential for these high-performance cutting tools for decades. But the research we're exploring today is all about finding alternatives to both of those materials. Why is this such a critical area of research right now?
Yeah, it's a question of looking ahead and really understanding the limitations of our current materials.
Right. What are those limitations?
It all comes down to raw materials. Both cobalt and tungsten are categorized as critical raw materials, meaning their supply chains are vulnerable, their availability can fluctuate, and their prices can be quite volatile. And there are a number of factors driving this.
Let's break that down a bit. What's happening with cobalt specifically?
So the demand for cobalt has just exploded in recent years. And the main driver of this surge is the booming clean energy sector and the massive global adoption of electric vehicles.
EVs, yeah, we all know how big that industry is becoming.
It's huge. Figure 1.9 in the thesis really highlights this. The data shows that a whopping 45% of the global cobalt demand right now is for EV batteries. And another 26% goes into portable electronics like smartphones and laptops. That's over 70% of the world's cobalt supply, tied to just these two massive industries.
Wow, that is a huge proportion. And even if the percentage used in hard metals in those cutting tools is relatively small, the overall pressure on cobalt supply must be immense.
Exactly. While only about 8% of the cobalt that's mined actually ends up in hard metals, as shown in Figure 1.9, the sheer scale of demand from those other industries, EVs and electronics, is driving prices through the roof. Figure 1.10 illustrates this pretty dramatically. The price of cobalt has just been skyrocketing.
So it's not just about the cost potentially going up, it's about the fundamental availability of the material itself, isn't it?
Precisely. And the projections in Figure 1.11 paint a concerning picture for the future. In a scenario where we achieve net zero emissions, which is the goal, right? Well, in that scenario, the demand for cobalt is projected to significantly exceed the available supply. That could lead to serious shortages and even more extreme price spikes.
That's a significant concern for any industry that relies on cobalt, including the tooling sector.
Absolutely. And that's why finding alternatives is so critical.
Okay, so cobalt is facing some serious challenges. What about tungsten?
Tungsten is also a critical raw material, though the situation's a bit different. It does have a relatively high recycling rate, over 25%, which is a positive.
That's good, at least.
But it's still designated as a strategic raw material, or SRM. And that's because it has such a wide range of applications, and in many of those, it's extremely difficult to find a suitable substitute.
Right, so even with recycling, we need to explore alternatives to reduce our dependence on it.
Exactly. And the thesis provides a good overview of where tungsten comes from and how it's used. The primary source is from minerals like wolframite and scheelite, and most of the global supply comes from a handful of countries, mainly China, Vietnam, and Russia.
So the supply chain for tungsten is also geographically concentrated, which makes it potentially vulnerable to disruptions.
Right, and Figure 1.12 breaks down the primary uses of tungsten within the European Union. As you might expect, the biggest chunk, 60%, goes into the production of tungsten carbides. But it's also vital for a whole bunch of other applications.
Like what?
Things like filaments in traditional light bulbs, various components in electronics, high-temperature furnace parts, even applications in aerospace and the military.
So it's used in things that require extreme durability, high hardness, and resistance to heat.
Exactly. And those specific properties make it very challenging to find suitable replacements.
That makes sense. So we're seeing potential supply vulnerabilities and price fluctuations for both cobalt and tungsten. And recycling alone isn't enough to mitigate those risks.
Right. And the thesis points out that current recycling methods just aren't efficient or economical enough to fully recover these materials.
So that brings us to the heart of the matter. What kind of alternative materials are being investigated, and how does this colloidal processing technique play into it all?
Okay, so since we can't fully rely on recycling, developing new material systems from the ground up is essential for the long-term sustainability of the tooling industry.
Right, and the researchers in this thesis are really pushing the boundaries with their approach.
Yeah, they're focusing on two key objectives: finding a viable substitute for cobalt as that binder material, and figuring out ways to enhance the overall properties of cutting tools so they last longer and require less material to begin with.
Makes sense. So what are some of the materials they're experimenting with?
Well, on the binder side, they're looking at alloys that don't rely on cobalt at all. They're exploring iron-nickel alloys in particular, and they're even investigating the use of pre-alloyed powders as a way to improve the performance of those binders.
Interesting. And what about the hard ceramic phase? Are they looking at alternatives to tungsten carbide?
They are. They're investigating titanium carbonitride, often shortened to TiCN, as a potential substitute for tungsten carbide. And this is where the colloidal processing technique comes in.
Okay, let's dive into that. What exactly is colloidal processing, and why is it so appealing in this context?
Colloidal processing represents a completely different way of thinking about how we make these materials. Instead of starting with dry powders, you use liquid suspensions of those powders.
Suspensions. So like imagine mixing flour and water to make a batter.
Kind of, but we're talking about much, much smaller particles. Think about milk. Milk is actually a colloid. It's a system where tiny droplets of fat are dispersed throughout a liquid, which is mostly water.
Ah, okay, I get it. So instead of mixing dry ingredients, you're essentially creating a special kind of liquid mixture.
Precisely. And the advantage of using this liquid-based method is that you have much finer control over the size of those particles and how evenly they're distributed within that liquid. You can also very precisely manage the viscosity of the liquid and significantly reduce the amount of organic binders needed later in the process.
So it's a more precise and potentially more environmentally friendly approach.
Exactly. Now, in this research, they're working with suspensions of either tungsten carbide or titanium carbonitride powders, along with metal powders like iron and nickel. And they're using water as the base liquid.
Okay, that makes sense. But how do they keep those tiny particles in the suspension from clumping together? I imagine they would have a tendency to do that.
That's a really important point.
Yeah.
To prevent that clumping, they need to create what we call a stable dispersion. They need those particles to repel each other and stay evenly distributed.
Right. How do they achieve that?
They use a combination of specific polymers and surfactants, which are essentially chemicals that alter the surface properties of the particles.
So they're adding these special ingredients to the liquid to keep the particles from sticking together.
Exactly. These molecules coat the surface of each particle, creating a barrier that prevents them from attracting each other. It's all about manipulating those tiny forces at the nanoscale.
So this particular research chose to focus on titanium carbonitride as a potential alternative for the tungsten carbide, and they used an iron-nickel alloy, a blend of 85% iron and 15% nickel by weight, as a potential binder to replace cobalt. Why those specific choices?
Their main goal was to explore direct material substitution. Titanium carbonitride has some properties that make it a promising candidate to replace tungsten carbide, and iron and nickel are both readily available and, crucially, much less problematic than cobalt when it comes to those supply chain and environmental concerns.
Okay, that makes sense. So they're not just experimenting with new materials, they're also exploring a fundamentally different way of putting those materials together, using this colloidal processing technique. And they chose that technique because it offers greater control over the manufacturing process and potentially makes it more environmentally friendly.
Exactly. It's about pushing the boundaries on both the materials themselves and the way we process them.
All right, let's get into the nitty-gritty of their process. What were the main steps involved in actually manufacturing these new materials?
Chapters 2 and 3 of the thesis go through it all in great detail, but Figure 2.1 gives a good visual overview. The first step is obviously to prepare those colloidal suspensions of the raw material powders, getting the right mix of materials and those dispersing agents in the water.
Right, so that's step one. What comes next?
The next key step is called atomization. This is essentially a process of transforming that liquid suspension back into a dry powder, but it's done in a very controlled way to ensure the particles are the right size and shape.
So it's like controlled drying to create a powder with specific characteristics.
Exactly. And that powder is then compacted into a specific shape through a pressing process. The compacted part is still quite fragile at this point. It's called a green body.
So it's formed, but it's not a solid, usable part yet.
Right. The final crucial step is sintering. This involves heating that pressed part to an extremely high temperature for a set amount of time to fuse those powder particles together, creating a solid, dense material.
It's amazing how they can manipulate materials at such a fine scale. What were the starting materials they used?
They started with commercially available powders, titanium carbonitride, tungsten carbide, iron, nickel, and they also added a bit of black carbon in some cases. And the thesis provides a lot of detail about the characteristics of those starting powders. Figures 2.2 and 2.3 show images of those powders, and Table 2.1 gives you all the specifics about their size and morphology. Interestingly, the titanium carbonitride had a more irregular angular shape, while the other powders were smoother and more rounded.
I see. And they had to carefully combine these powders in water to create those stable suspensions, right? What were those special additives they used to achieve that?
They used deionized water as the base liquid, and then they added specific chemicals to help the particles disperse and remain stable. These included tetramethylammonium hydroxide, HTMA, hydroxypropyl methylcellulose, HPMC, TPMB glycol ether, and polyethylenamine, PEI.
Those are some serious tongue twisters, and it sounds like they put a lot of effort into optimizing the proportions of those additives to get the best possible suspension.
They did. The thesis mentions that the specific ratios they used were based on previous research. So they weren't starting completely from scratch, which is always helpful in research.
Absolutely. Okay, so now they have those carefully prepared suspensions. Let's talk about the atomization process in more detail. What exactly happens during that step?
Figure 2.4 shows a schematic of the setup. It involves spraying the liquid suspension through a very small nozzle. They used one with a 1 millimeter opening into a heated chamber. The chamber is filled with hot air, which rapidly evaporates the water in the droplets. As the water evaporates, you're left with these tiny dry powder particles.
So it's a carefully controlled drying process, essentially.
Exactly. They used a temperature of 200 degrees Celsius and a controlled airflow of 32 bar. This process created a mixture of fine and slightly coarser powders, which they combined in specific ratios for the next stage. Figure 3.5 shows images of those atomized powders. Many of the particles had a nice spherical shape, which is good for the pressing stage because it allows for better packing.
Makes sense.
There were also some particles with slight imperfections, little dimples or depressions. This is pretty common in ceramic atomization, and it happens because of the way the droplets dry. Sometimes they form hollow particles that partially collapse.
So even at this microscopic level, there are these little imperfections that can occur. Fascinating. Did they analyze the size of those atomized powders? I imagine that would be important for how well they eventually bond together.
Absolutely. They did detailed particle size analysis to understand the range of sizes they had. And there's a general guideline in powder metallurgy that for optimal sintering, the ratio between the smallest and largest particle sizes shouldn't exceed 1 to 10.
Okay, so there needs to be some consistency in size.
Right. And Figure 3.7 and Table 3.2 present their findings. For the tungsten carbide iron nickel material, they found a pretty uniform distribution of particle sizes, with an average size around 16 micrometers. But for the titanium carbonitride iron nickel powder, there were actually two distinct groups of particle sizes, one around 7 micrometers and another around 19 micrometers, so a bit more variability there.
Interesting. So they now have these powders with specific characteristics. How did they transform those loose powders into those solid, usable parts?
That involved the two final key steps, pressing and sintering. The pressing stage involved compacting the powder into a specific shape using a technique called uniaxial cold pressing. They basically put the powder in a mold and apply a lot of pressure. The resulting part is still quite fragile, but it has the desired shape.
Right, it's that green body we talked about.
Exactly. Then comes the sintering stage. They heat that pressed part to a very high temperature, in this case, 1450 degrees Celsius for 2 hours in a controlled atmosphere. And this is where the magic happens. That intense heat provides the energy for the individual powder particles to bond together, forming a solid, dense material.
So it's like baking a cake, but at a much, much higher temperature. And they experimented with different atmospheres during that sintering process, right? What's the reason for that?
Yeah, Chapter 4 of the thesis focuses on that. The atmosphere during sintering plays a crucial role. You need to protect the material from oxidation at those high temperatures, promote good bonding between the particles, prevent unwanted chemical reactions, and potentially help to remove any residual organic materials from the previous steps.
So it's like creating the perfect environment for those particles to fuse together in the best possible way.
Exactly. And they tested 3 different atmospheres, a mixture of nitrogen and hydrogen, N2H2, vacuum, and pure argon gas. They basically ran the sintering process 3 times for each material, each time with a different atmosphere, and then compared the results.
Makes sense. It's a systematic way to figure out what works best. Did they do anything special to prepare the pressed parts before sintering?
They did compressibility studies beforehand. shown in figure 4.1, to figure out the optimal pressure to use during the pressing stage for each material. This ensures that the green part has a good density before it even goes into the sintering furnace.
So they optimized every step of the process. What were the key findings when they compared the effects of those different sintering atmospheres?
They looked at things like hardness, which is shown in figure 4.12, and the amount of porosity left in the final material. They found that sintering in the hydrogenated nitrogen atmosphere resulted in lower hardness, and they discovered that some unwanted chemical reactions had occurred, which explains the reduced hardness.
Okay, so hydrogenated nitrogen was out. What about the other two?
Well, the results for vacuum and argon were actually quite similar in terms of hardness, but for the titanium carbonitride iron nickel material, sintering in argon resulted in slightly higher hardness and less porosity compared to vacuum. Ultimately, they chose argon as the best option, both because of the properties it produced and because argon is already widely used in industrial settings.
So argon emerged as the winner for sintering. They really did their homework, testing and optimizing every stage of the process. But the real test is how those manufactured materials actually perform. What happened when they put them through those rigorous tests?
Chapter 5 of the thesis dives deep into that, and it's packed with data. They did a ton of characterization. First, they looked at the microstructure of the materials using scanning electron microscopy. The images in figure 5.1 show what those structures look like.
Cool. And they compared their materials to a standard reference material, right?
Yeah, they used a commercially available tungsten carbide alloy with 12% cobalt, the WC-12Co, as their benchmark.
Yeah.
They wanted to see how their new materials stacked up against the industry standard.
Makes sense. And what kinds of tests did they do?
Oh, a whole bunch. They tested flexural strength, fracture toughness, hardness, thermal diffusivity, thermal conductivity. They even looked at their tribological behavior, which basically means how they perform under friction and wear. And they did all these tests at various temperatures, ranging from room temperature up to 800 degrees Celsius.
Wow, that's a comprehensive evaluation. And how did they perform? Let's start with those mechanical properties. What happened to their strength and toughness as the temperature increased?
Figures 5.2 and 5.4 show the results for flexural strength and fracture toughness. They found that both of the new materials, the tungsten carbide iron nickel and the titanium carbonitride iron nickel, started to lose strength and toughness above 400 degrees Celsius. The standard WC-12Co actually performed a bit better at higher temperatures, with its properties dropping off more significantly above 600 degrees. This suggests that oxidation is playing a role at those higher temperatures.
So high temperatures are still a challenge for these alternatives. What about those fractured surfaces? Did they analyze those to figure out how the materials were failing?
They did. They used scanning electron microscopy to examine those broken surfaces, and it revealed a really complex picture. At lower temperatures, the fractures looked brittle overall, meaning the materials tended to crack rather than deform. But when they zoomed in, they found evidence of ductile fracture in the iron-nickel binder and both intergranular and transgranular fracture in the ceramic phases. And sometimes there was even delamination happening between the binder and the ceramic particles.
So a mix of different fracture mechanisms at play.
Yeah, but importantly, they found that the bonding between the binder and the ceramic was generally quite strong. And that's a good thing because it means that those cracks don't propagate as easily. The strong bonding helps to deflect them and dissipate energy.
So even though they might fracture, they don't just completely fall apart. That's a positive sign. What about hardness? How did their hardness compare to the standard WC-12Co?
Figure 5.13 shows the results for hardness as a function of temperature. The WC-12Co consistently had the highest hardness across the entire temperature range. They think this might be partly because the reference material contains small additions of zirconium and yttrium oxides, which are very hard and stable at high temperatures. Interestingly, though, the titanium carbonitride iron nickel had a room temperature hardness comparable to another reference material from a previous study, which was a good sign.
Okay, so the WC-12Co still holds the crown for hardness, but the titanium carbonitride iron nickel is showing promise. What about those thermal properties, their ability to handle heat?
Figure 5.15 shows the results for thermal diffusivity and conductivity. And it's interesting because the trend really depended on which ceramic phase they were looking at. For the tungsten carbide-based materials, the ability to transfer heat actually decreased as the temperature went up. But the titanium carbonitride iron nickel had a much more stable thermal conductivity across the whole temperature range.
So they behave differently when it comes to heat. Finally, what about wear and tear? How did they hold up in those tribological tests?
So figure 5.16 shows the results for friction coefficient and wear rate. At room temperature, the tungsten carbide iron nickel actually had the lowest friction, which is good. And the wear rates were similar for all three materials at room temperature. But when they crank up the temperature to 200 degrees Celsius, the friction increased for all of them, which means more wear.
Makes sense. High temperatures are tough on everything. Did they look into why that wear was happening?
They did. They used scanning electron microscopy and energy dispersive X-ray spectroscopy to analyze the wear tracks. Figures 5.19, 5.23, and 5.28 show some of those images. They found that the main mechanisms at play were abrasive wear, adhesive wear, and oxidation-induced wear. And they even observed material transfer from the testing apparatus onto the cutting tool surfaces.
Wow, so it's a complex interplay of different wear mechanisms happening at the microscopic level.
It is. So to sum it all up, Chapter 6 lays out their main conclusions.
Okay, let's hear it. What are the key takeaways from all this research?
Well, they reiterate the growing demand for and the criticality of both tungsten and cobalt, and of course the fact that cobalt is toxic. These are the driving forces behind this search for alternatives. They highlight the success they had using HPMC as a more sustainable dispersing agent in their colloidal processing.
Right, and they confirmed that argon was the best sintering atmosphere?
Exactly. And for the mechanical properties, they found that the iron-nickel matrix was actually better than cobalt's below 200 degrees Celsius because it's more ductile, more flexible. But above 400 degrees, the iron-nickel starts to degrade, and the WC-12Co performed better. And at that super high temperature of 800 degrees, all of them really struggled.
Yeah, high temperatures are a tough nut to crack.
They are. But on a positive note, the new materials showed good tribological performance. Lower friction at 25 degrees Celsius compared to the reference.
So a mixed bag, but some promising results overall. And it sounds like they developed a very sophisticated process for creating these materials.
They did. They successfully made tungsten carbide iron nickel and titanium carbonitride iron nickel composites using colloidal processing and optimized sintering. It's a real testament to the power of material science.
Absolutely. For all of you listening, we hope this deep dive has given you a good understanding of the challenges facing the cutting tool industry and the potential solutions that are being developed.
It's a fascinating area of research, and it has huge implications for all sorts of industries.
It really makes you think about the future of manufacturing. Considering the need to balance performance, sustainability, and cost, what future innovations do you think will be most critical for the evolution of industrial materials? What will the cutting tools of tomorrow be made of? It's a question worth pondering.
It is. And the findings of this research open up all sorts of avenues for future exploration. We encourage you to think about what this means for different industries and maybe even dive deeper into the research yourself. There's always more to learn.
Exactly. Material science is a constantly evolving field, and it's playing a key role in shaping our technological future. Thanks for joining us on this deep dive. We'll catch you on the next one.
See you then.